And then let's proceed into session 3, adversarial machine learning and trustworthiness. The first paper there is adversarial robustness for face recognition, how to introduce ensemble diversity among feature extractors. So I open the floor for that paper.
Okay.
Yes, well, welcome to Kuma. Are you able? Okay, great. I see.
Yes. Can you see my slide?
Yes, we can.
Yes. Okay. Okay. Hello, everyone. I'm Takuma Amada from NEC Corporation. This is a joint work with Kazuya Kakizaki, Toshinori Araki, Senpei Ryu, Joseph Keshet, and Jun Furukawa from NEC and Barilan University. Okay, let me start from the introduction of adversarial examples in deep learning. Deep learning is useful for many applications, including security critical services, such as face recognition system. Adversarial examples are inconceivably perturbed input that can deceive deep learning. This is the scenario of attacking face recognition system. The attacker can craft AX from the source image so that AX can be recognized as the target image. A human can distinguish AX and target image as a different identity, but face recognition can be deceived. So, deep learning-based security critical services is not reliable under attacks by AX. So many methods of preventing AX have been proposed. Adversarial training and ensemble diversity promotions are the most successful method among them. Adversarial training generate AX and use them in the training phase. The adaptive diversity promoting method, this is called ADP, promotes the non-maximal predictions of multiple models to be diverse. The figure sketches the ADP method. The ADP trains multiple models with a regularizer that makes a volume spanned by vectors of the maximal predictions of each model large. So this regularizer promotes the diversity of the maximal predictions. The ADP method makes it hard to perturb an input that increases any specific non-maximal predictions of different models simultaneously, and thus make the model robust against AX. However, neither adversarial training and nor ADP is sufficient yet, and more improvement is necessary. A feature extractor is useful to classify inputs whose classes are unknown at the time of training. Such a scenario is particularly useful for many of commercial face recognitions, and they usually rely on the feature extractor. We commonly train a feature extractor as a part of classifier. Once we train a classifier, we remove its finally connected layer to the predictions of classes. And we use the remaining convolution network as a feature extractor. So the feature extractor can recognize whether or not two inputs are in the same class by measuring their distance in the feature space. A promotion of ensemble diversity is one of the effective methods for preventing AX. However, it has not been applied to feature extractors. So here is our problem and goals of our method work. We preliminarily applied the adaptive diversity promotion method to train face recognition directly. But our experiment shows that ADP did not improve the robustness to AX at all. So our goal is to find how to introduce the ensemble diversity to feature extractor in the right manner and obtain the face recognition that is more robust to AX. Also, we expect our method eventually helps more deep learning applied to security critical infrastructures. So if we see the inside as our diagnosis, if we see the inside of the loss function, it is like this. The value of losses are determined by the angle between normalized weights and also normalized feature vectors. So only the angles are essential. Suppose we have two models with different features vectors, like this left sketch. If the weight vectors are at the same angle, then the difference of feature vectors has no effect to the loss. This is what's happening in the direct application of ADP method. So in our method, we let the weight vectors in different models the same, like red colored vectors. Then we can see that if feature vectors are in different direction, their angles to weight vectors are different. So for our method, this is the structure of our method. We propose to share the weight vectors of the last layers among the all models in the ensemble. Since the directions of weight vectors are the directions of the feature, the diversity of feature vectors with respect to the common weight vectors introduces meaningful diversity among features. In addition to the sharing of weight vector, we directly promote the diversity of feature vectors instead of non-maximal predictions of the classifiers. So this is the experimental setting to compare our method with existing methods. We use MS1 MV2 dataset for training and use VGG2 dataset for test. And the number of models in the ensemble is 3. We adapt the mobile face net for the network architecture. As attack strategy, we utilize the ROTS method via 3 attacks: iterative FGSM and basic iterative method and Karini-Wagner method. We adapted these attacks until the impersonation attack is successful. And to evaluate the robustness of feature extractor, we measured attack success rate by AX with different size of input perturbation or feature distance. So this is the comparison of validation accuracy by single model ADP method, adversary training, and our method for legitimate data. Also, we tested in various datasets, LFW, CFP-FP, and HDB30. So we can see our method does not decrease the accuracy for legitimate data. Okay, and this is the result for white box attack. We compared attack success rate for different perturbation size. So the horizontal axis is the perturbation size of L2 norm, and the vertical axis is the attack success rate. So when the graph is plotted lower, it means more robust. So red colored plots are our method. So from this graph, our method is most robust in white box attack. Okay, and evaluation result against the BIM and CW is the same tendency of iterative FGSM. And this is the result for black box attack. We compared the success rate for AX to the single model with different distances in feature space. So we generate adversarial examples from single model in white box setting, and we transferred them to the different models and measure the attack success rate. This graph shows that also this graph, the graph is plotted lower. It means more robust, as well as the white box experiments. So we can see our method is most robust under black box attacks. So as a conclusion, a feature extractor is essential for face recognitions, and promotion of ensemble diversities are one of the promising methods to prevent AX. However, we could not apply ADP to feature extractor directly. So we presented how to introduce ensemble diversity among feature extractors for robust face recognition without compromising the accuracy. So our method shows better robustness compared to adversarial training, although the variation is not birthday as others. Thank you.
Thank you so much. That was great. We will have a debate panel at the end of the session, so everybody remember your questions for later. For now, we'll be moving on to the next paper. Multimodal generative adversarial networks make realistic and diverse but untrustworthy predictions when applied to ill-posed problems. I open the floor for this paper.
Hi, can you hear me?
Yes. Hi, John.
Hi. Do I just share my screen and have the presentation open on another tab, or is it online somewhere? Because I know I had to submit it.
I believe you can just share your screen.
Okay. One moment. Let's see. Can you see that?
Yes.
And is it full screen now?
Yes, it is.
Okay. All right. So it's now good?
Please.
All right. So hi, I'm John Hyatt. I'm going to be talking about generative networks and how they can provide, as he said, realistic and diverse predictions that are still untrustworthy. And this is work done with my team lead, Mike Lee, at the U.S. Army Research Laboratory. So everyone here is probably familiar with generative models. Just a quick refresher, one way to think about them is basically a way to convert a representation in latent space, which is basically a collection of vectors that represent different features in your model or in your data, to data space. So for an image, that might be pixel values and locations, different collections of features. For audio, it could be different sounds, stuff like that. There are many different types of generative models. The two most common are probably generative adversarial networks and variational autoencoders, which have been around for quite some time, and there's 100 different variations of each of those. Autoaggressive models like Transformer are much more recent, but they've done some pretty impressive stuff. And invertible neural networks are probably the least well studied of these. I'm going to mention them very briefly at the end. So a quick refresher on GANs. Again, everyone here is probably familiar with them, but just in case, there are two models, a generator and a discriminator, where the generator takes some latent space vector and generates an output in data space. The discriminator looks at different data space images and decides whether or not they are something the generator created or whether they're from the true data distribution. And by taking information from the discriminator and feeding in an adversarial loop, the generator eventually learns to create more and more realistic images. And so the idea is at the end of this process, you can feed it a latent space vector and it will generate some realistic image that is indistinguishable from a real one. Variational autoencoders also have two models. They're trained sequentially. You take a data space point X, feed it into your encoder, which encodes that image or whatever other input you have as a distribution in latent space, not as a point, but as a distribution. You then sample from that distribution, feed those latent space points back into the decoder, the second model, and that attempts to reconstruct the original data space image. After training, if your encoded distribution looks like some simple prior, like Gaussian, you can just sample from the Gaussian and use the decoder as your generative model. So it turns out that when you try to extend this to conditional problems where you have some partial information, some conditioning information, why that you want your answer to be consistent with, it's more difficult to get multimodality. So a simple application of just adding in stochastic noise and a conditioning information to a problem, you tend to get the same prediction for a given y every time, which isn't very helpful. People have done work on this. So this is a paper from a few years ago about a model called Bicycle GAN, where basically they resolved this problem by combining different aspects of conditional GANs and VAEs, which is why I mentioned those. And it's able to create a one-to-many map that produces realistic and diverse outputs. So this is a fairly complicated problem. Basically, they trained it to take input images of nighttime and convert those to daytime images. As you know, if you take a particular image at night and you come back the next day, it could be cloudy, it could be overcast, it could have clear skies. You know, the darkness prevents you from seeing certain things like mountains in the background, different foreground, different lighting, shading, all that kind of stuff. So this model was able to create realistic and diverse images, but there was some stuff in the paper that didn't cover, as well as other papers looking at the same problem, such as how well it actually did represent the true possible distribution of, in this case, daytime images. And that's something that we're interested in. And this type of problem is one type of ill-posed problem. And ill-posed problems are something that show up all the time in machine learning. So a problem is ill-posed if it doesn't have a solution, which should remind you of out-of-distribution classification problems. It's ill-posed if the solution is not a continuous function of initial conditions, like adversarial examples where a small change to the input can produce a large change in the output. And it's ill-posed if the solution is not unique, which is the case here. So this is sort of like a subset of a much broader class of machine learning related problems. And the thing, as I said, that we're most interested in is whether or not the distribution of predictions that the model creates is trustworthy, is representative of the true data distribution that we're interested in. For a lot of generative problems, I don't really have a good word for this, but you might say aesthetic is kind of the desired result. You know, those apps that you see on your smartphones where you can take your face and convert it to a cartoon or something like that, just creating, removing different features from an image, making, you know, audio sound a little bit less noisy. The thing you care about the most is whether or not the result is plausible. But if you have a highly uncertain problem where you have a little bit of information, but there's a lot of uncertainty, and you want to use that to some application that has a stringent criterion where you have, like, you know, risk management, uncertainty quantification, some downstream decision-making process where whatever your final model prediction is going to have an impact on the real world. You want to be able to say, okay, we're going to see these features with some probability, we're not going to see these features, and by feeding in this noisy, uncertain information, you can get a pretty good idea of what the actual possible true data point that you're looking at is. And what that kind of means in practical terms is that we want a way to bijectively map between latent space and data space. And the reason for this is because latent space is something that we can sample easily if we choose a prior correctly in our model. Data space is hard to sample from because it's many dimensional and the real world is a mess. And we want to be able to do this for some partial conditioning information y that basically tells us something about our problem, but not enough to make a unique decision. And this kind of thing shows up in a lot of different applications. Extreme super resolution, not where the image is a little pixely, but where it's been so downsampled that everything is just, the features are just lost and have to be reconstructed. Denoising audio, denoising radio, basically anything where you've got corrupted inputs. And we want to be able to sample from our latent space prior, feed different points into the model, and then say this is equivalent to sampling from the true conditional distribution of data points consistent with our conditioning information Y. And at the end of this, we want to be able to know that this distribution is the correct distribution, and we can trust it when we're making our decisions in the real world. So the starting point that we used was that same paper that I showed an image from before, Bicycle GAN. Basically, as I said, they combined the different models from variational autoencoders and generative adversarial networks. There's a generator that takes conditional information Y, a latent space vector Z, and uses those to generate some data set point X. There's an encoder that goes the opposite direction, but you'll note that it's not symmetric. It doesn't have the conditioning information as an input, so it's just trying to go from data space directly to latent space. And then a discriminator whose job it is to make the generator learn realistic outputs. And without writing down a bunch of math, it's optimized on whether or not the generator can produce realistic outputs, whether or not the two models can invert one another. So if E of G is the same as the original input and vice versa, and whether or not, as with the variational autoencoder, the encoder outputs a point cloud that's close to our desired prior distribution. So as I said, this is kind of asking the generator and the encoder to invert one another, which I'm mentioning because it's going to lead us into looking at invertible neural networks later. But there are some issues with that. The encoder has no conditional input. As with the VAE, it's outputting a point cloud rather than a point, so you can't directly compare the starting and end points when you try to invert the model. And I'm not going to go into the details, but the training in that architecture is not symmetric for the two. And furthermore, in addition to that, there's no direct examination of how accurately those learn the target distributions, which again is not an indictment of the paper or any of the other ones that looked at the same problem, because you can see the results here are pretty impressive and they are realistic and they are diverse. So at the very least, they're a subset of the desired distribution. We also, what we found was that we weren't able to produce the desired distributions looking at that using the original model. So we made changes. We looked at different hyperparameters. We made the encoder symmetric, so it also has the conditioning information and can hopefully learn to disentangle the conditioning information in latent space contributions. We made it deterministic and evaluated distribution statistics on a batch rather than looking at a point cloud. We split the cycle consistency losses, so the invertible losses between the two models, so they could be trained symmetrically. And what we found is that even after all this, they never were able to learn one another. So we focused on a really simple problem just to see where we could start with, but it turned out being a lot deeper than we had originally anticipated. We never moved beyond that simple problem. This is an image from the Fashion Eminence dataset, which is a collection of clothes, shirts, shoes, pants, stuff like that. This is a low-res image of the shirt on the left that has been downsampled to a featureless blob. And then we feed this featureless blob into our model that's been trained on the entire data set along with latent space points, and we are able to generate realistic and diverse reconstructions, but they're not representative. If you look at the latent space representations of these things, the red is a bunch of points from the true Gaussian distribution that we wanted to map to. Black is the much narrower learned distribution, and basically what this means is that the model is sampling only from a small subset of the true data space X. And so they are realistic, they are diverse, but they don't represent the true distribution. And that's kind of the big takeaway here, is that even if you have realistic and diverse outputs, you shouldn't assume that the model has learned your true distribution, that it's representative. And kind of as an aside end of this, these model pairs are kind of hard to train, and we think it makes more sense to look at explicitly invertible models like invertible neural networks, which I don't have time to talk about. But basically, we have some very preliminary results, and we think they're very promising. Thank you.
Awesome. Thank you so much, John. Our next paper on the doc here, deepfakes on physics. Deepfakes detection based on, oh, wait, I'm sorry. Yes, the deepfake detection based on heart rate estimation.
Hello, I'm going to, can you hear me?
Yes, Javier, how are you?
Okay, fine, thank you. I'm going to share you my screen.
Please. Yes, we can see.
Okay, it's okay? Okay, thank you. Hello everyone. My name is Javier Hernández. I'm a researcher from Vida Lab. and I'm here to introduce you deepfake on FIS, a deepfake detection method I developed in collaboration with Rubén Tolosana, Julián Fierrez, and Adb Morales, all from Universitat Autónoma de Madrid. Well, a brief introduction. The popular term deepfake is usually referred to a deep learning-based technique that is able to create fake videos, swapping the face of a person by the face of another person. This type of manipulation is also known as identity swap, and the research in this field is moving forward very fast. Currently, most face manipulation are based on machine learning techniques like autoencoders and generative adversarial networks, achieving generally very realistic visual results, especially in the latest generation of public deepfake databases. Here in the slide, we can see an example of a realistic deepfake in which the face of Robert De Niro is swapped by the face of Al Pacino. In physical face attacks, there is presentation attacks. Real subjects are impersonated using artifacts such as photographs, videos, and masks. Face recognition systems are known to be vulnerable against this type of attacks. And specifically for detecting 3D mask impersonation, which is one of the most challenging type of attacks, texture and shape-based techniques are not efficient, and other approaches are necessary. So detecting pulse or head rate from face videos using remote photoplethysmography, RPPG, has shown to be an effective countermeasure against 3D masks attacks. When applying this technique to a video with a fake mask, the estimated heart rate signal is significantly different to the heart rate and that can be extracted from a real face. So we think that deepfakes are manipulations somehow similar to a physical 3D mask, are somehow a digital version of this 3D mask. So to the best of our knowledge, we think that deepfake techniques, current deepfake techniques, do not emulate the physiology of human beings. For example, the heart rate or the blood oxygenation, the breath rate. So that's why in this work, we hypothesize that the fake detectors based on physiological measurement can also be used against deepfakes after adapting them properly. So our approach here consists in using that RPPG features that have been previously learned for the task of heart rate estimation using real face videos and adapting them for the detection of deepfakes by means of a knowledge transfer process, thus obtaining a novel fake detector based on physiological measurement that we name deepfake on FIS. Our physiological detector intends to be a robust solution to the weaknesses of most state-of-the-art deepfake detectors that are based on the visual artifacts, fingerprints, texture and shape artifacts inserted during the synthesis process. So our fake detection approach is based on the original architecture of called DeepFIS of Chen and McDermid. That is conformed by a convolutional attention network. There is two parallel CNNs, convolutional neural networks, that are able to extract spatial and temporal information from video frames. In the next slides, I'm going to describe the different stages of this convolutional attention network and the changes we made to the original architecture and the training process for adapting it to the deepfake detection problem. The first stage of the framework consists in a preprocessing stage to prepare the images from the video to feed the convolutional attention network. The system receives the frames from the video and detects crops and aligns the faces using the MTCNN face detector. For the rest of the video, it tracks the detected face using the KLT feature tracker. We compute a normalized frame that is the cropped and aligned face, but first downsample to 36 pixels by 36 pixels and normalize to zero mean and unitary standard deviation for higher convergence speed of the training process. And after that, we compute the normalized frames difference that consists of a new frame compute as the normalized difference of the current normalized frame and the previous normalized frame. That frame difference will be a representation of motion and changes in the illumination during the video. The second stage of the framework consists in the proper convolutional attention network that is composed of two different branches. The first CNN branch is the appearance model. This branch focuses on the analysis of the static information of each video frame, and it has the target of providing the entire network with information about which points of the current frame may contain the most relevant information for detecting deepfakes. The input of this branch are the normalized frames. And the other branch of the network is the motion model that has been designed for detecting changes between consecutive frames. And that is performing a short time analysis of the video for detecting the deepfakes. The input of this branch are the normalized frame difference, and it also uses the attention information provided by the appearance model, since the attention masks coming from the appearance model are shared with the motion model at two different points. Finally, the output layer of this motion model is also the final output of the entire network. And since we do not aim to estimate the heart rate of the subject, but we want to estimate the presence of a deepfake face, we change the final regression layer and fully connected layers with a new fully connected layer of 128 elements and a final classification layer using a sigmoid activation function for obtaining a final score in the 0 to 1 range for each instant of the video, each frame, that is related to the probability of the face being real or being a deep fake. Two different public databases are considered in this experimental framework. In particular, CelebDF version 2 and DFDC Preview, that are two of the most challenging deepfake databases up to date. Their videos exhibit a large range of variations in several aspects, such as face sizes, lighting conditions, background, acquisition scenarios, distancing from person to the camera, and so on. So these databases present also enough images, both fake and genuine, for fine-tuning the original weights of the model that were meant for heart rate estimation, and adapting them and obtaining new weights also based in RPPG, but adapted for deepfake detection. Well, as I have said previously, deepfake on FIS is based on DeepFIS architecture, that is a deep learning model trained for heart rate estimation from face videos based on RPPG. However, the DeepFIS model is not publicly available, so we decided to initialize the weights of deepfake on FIS with the weights from another model based on DeepFIS, also pre-trained for heart rate estimation, that were presented in our own paper for heart rate estimation. And we trained it with a public database that is CoFace database. So we take the weights from this own implementation of DeepFIS, and we initialize the weights of deepfake on FIS. Then the training databases have been divided into non-overlapping datasets, one for development and other for evaluation. It's important to remark here that the evaluation was carried out at frame level, not at video level. As we mentioned before, we changed the final full regression layer of the original model by a fully connected layer and a classification layer with a segmented activation function to estimate the probability of a face being real or a fake. Okay. Then we initialize the fake and face with the mentioned pre-trained weights. We freeze the weights of all the layers of the network apart from except the new classification layer and the last fully connected layer, and we retrain the model for 100 epochs, and we choose the best performing model based on validation accuracy over the evaluation dataset. We train, I want to remark that we train one model per training database, one model for CelebDF version 2 and other model for DF-DC preview. And this table shows the fake detection performance results we achieve in terms of area under the curve and accuracy over the final evaluation dataset of CelebDF version 2. And this other table shows the performance, the accuracy we achieve in the same terms, but for the DF-DC preview dataset. In general, very good results are achieved in both deepfakes databases. For the CelebDF version 2 database, deepfake on face achieved an accuracy of 98.7% and an area under the curve of 99.9%. And for DF-DC preview database, we achieved 94.4% of accuracy and 98.2% of area under the curve. And well, also in both tables, we compare the present work deepfake on face with other state-of-the-art deepfake detection approaches. I have to note that the comparison is not made always under the same dataset and protocols, so it must be interpreted with care. But despite of that, it is patent that the proposed deepfake on face method has achieved state-of-the-art results in both evaluation databases. Observing the results, it seems clear that our fake detector has learned to distinguish the spatiotemporal differences between the real and the deepfake faces of the training and evaluation databases. Our method has outperformed other popular fake detectors based on pure deep learning approaches, such as exception and capsule networks, and also other recent physiological approaches based on SVMs and convolutional neural networks. Since all the convolutional layers of deepfake on face were frozen before training it, and we only trained the last fully connected layers, we can conclude that the proposed detection approach, originally based on physiological measurement, is successfully using that pulse-related features for distinguishing between real and deep fakes. The results prove that current face manipulation techniques do not pay attention to the heart rate related physiological information of the human beings when synthesizing fake videos. Our future work will be oriented to the analysis of the robustness of the proposed fake detection approach against face manipulations unseen during the training process, other methods, other algorithms, other databases. We also want to apply temporal integration of frame data of the scores, the different scores, to analyze that scores along the video, and therefore being able of taking more reliable decisions. And well, finally, another option might be the application of this proposed physiological approach to other face manipulation techniques, such as face morphing, where two different faces are combined. With this, I conclude my talk and thank you for your attention.
Thank you so much, Javier. Great. So at this point, let's enter into the debate panel. So in addition to the three presenters, or actually, I guess the four presenters we just had, we could introduce, we can include Cynthia if she would like to participate. But in addition to the paper presenters, we also have José Hernández-Orallo and V.A. Vakuri. And let's jump into that. Jose, would you like to kick it off?
Okay, hello everybody. Well, I can start with the last presentation. I'm sorry I joined a little bit late and missed a little bit of the invited talk. Yeah, but maybe I will have a question for that one as well. But for the moment, I have a question about deepfakes with a heart rate detector. My question is, okay, this is a very good idea, and this works well when we try to detect deepfakes from the original videos or images. I think videos in this case. But what if I do some slight modifications of the original videos, which are not deepfakes? So even if just change the video rate, for instance, or I just use some traditional filter where the heart rate is more difficult to get, how do you know? You know that the image has been manipulated, but you don't know if it's a deepfake. So the question is, do you specifically detect that the video has been manipulated as a deepfake, or you just detect that the video has been manipulated?
Okay. Well, we didn't make any proof or any experiment related to other manipulations, but our model was originally trained for extracting features specifically for heart rate estimation, and the features of the last layers were combined to obtain a temporal signal that represents the heart rate. So if you manipulate the original video, for example, accelerating that video or another manipulations, in the model will extract another signal that for example, if you accelerate the video, it will extract a heart rate, a higher heart rate. If you, for example, blur the original video or introduce another artifact, maybe it will extract a signal that doesn't represent at all a heart rate. So with the modifications we made for detecting deepfakes, the only thing we're doing is distinguishing between two classes that I think I have to remark that we didn't make any check about this, any experiment, but I think that our model is distinguishing between a real heart rate signal between inside a range, for example, inside a range of BPMs, beats per minute, with components in specific frequencies, is distinguishing between this type of signals and each all the remaining signals that doesn't represent a heart rate. So maybe if you modify the original video just a little, the signal or the video will, the algorithm will be capable of extracting a heart rate signal. But if you modify it too much, for example, adding too much blur, it will detect it as a deep fake because it is not going to be able of extracting a heart rate. So it will classify it as a deep fake, even though it's not a deep fake.
Yeah. Yeah, I think it's clear that you focus more on the false negatives and the false positives here. A false positive situation, it is not a deep fake, but somebody has modified the images in some way, and then of course you have to check that there has been corrupted in some way, and somebody should look at this, and perhaps it's not a deep fake, it's another problem, or maybe sometimes you will have a kind of a false positive with some kind of a very harmless filter or something like that. But do you think that perhaps if we take the original videos from a different distribution, you might have a problem here? Or do you think that that's robust to original videos from a different distribution?
Well, I don't know what do you mean with.
So you have a collection of videos, and you train your deep fake for that, and you train your heart rate detector from that distribution. And now you take another distribution, and maybe in the new distribution, maybe you get a higher number of false positives or false negatives as a result. I don't know. You have try this, or you have any expectation? Of course, if the distribution is very different, you're going to get a little bit worse results. But my question was,
we try to training the model with videos created with a deepfake method, and which we test with videos created with another deepfake technique. And yes, it increases the false positives because it still works, but I think our training process is currently overfitting a little too much for each training database, the distribution of the videos of each training database. So it is generally in the deepfake literature, in the state of the art, is still a open problem how to generalize better between videos with different distribution of different methods, techniques. So.
I think it's a brilliant idea. Of course, there's always everything is in this area. Research is adversarial at any point. Whenever you try to find a solution, there's always an area that is not completely covered. But I think it's a great work. Okay, maybe some others might have questions.
Yeah, I might have one bridging question for the first and the third paper. So when we're talking about this dealing with robustness and raising it with these methods, so do you see that there, especially for the first paper, that we could have the maturity where the robustness is in a such high level that we could be taking, because many of these show the weaknesses of the facial recognition, and we can easily find weaknesses by these adversary attacks. So do you see that we can have such a high level of maturity on the robustness that this can actually be used? For example, just coming back to the last paper, we can easily see that, okay, now you're focusing on the physical side. It could be maybe easily added as a way of attacking by involving the physics also.
So the question is the metric for the compare the method and existing method, right? Sorry.
Yeah, the question is in short is, what is the future of the robustness in face recognition?
Yes.
Yeah.
So sorry, what was the question? Can you say again?
So what is the future for the robustness of face recognition? Because these, I would say, adversary examples easily show how these systems can be attacked, and the robustness is, and in many cases, it's easily, if you know the way to do it, it's easily the robustness is not considered as it is. It's breaking apart.
Okay. So basically, experiment. In experiment, we continue to attack until the attack is successful. So we measure the attack success rate. We measured the perturbation size to succeed to attack. So if we need more perturbation to succeed the attack, such models we can say such model is robust. Is it clear?
So by that metric, you consider the model robust enough?
So I have a brief comment on that. Can you hear me?
Yes, well and clear.
Yeah. So just regarding deep fakes and face recognition specifically, I know some work that people have been doing recently is looking at facial micro expressions and stuff like that, and doing automated detection of those, because even if you do a deep fake where you put someone's face on someone else, the gestures they have and the expressions that they use are usually pretty distinct from person to person, and those are replicated over the deep fake. And I know that at least there's at least a DARPA program looking into that. I know that they've had some success in distinguishing deep fakes based on that alone, and that is something I think would be pretty hard to fake without just recreating the entire features in the video, for example.
Okay.
Yeah, I had a question for John. This is a very general question. How do you measure diversity? I think I missed that. I think it's so important for you, but I missed that detail.
Yeah, so the way that we do that is just map back into latent space, because for the same reason that it's easy to sample from latent space and then map into data space. If you map your data space into your latent space, it's easy to look at the distribution of what you have relative to whatever prior you're planning to sample from. And if there's a mismatch between those two distributions, particularly if one is like a sub-distribution of the other, then you know that you're not looking at the full space because your model has not learned to map between them bijectively.
That's completely automatic.
I'm sorry?
That's completely automated. There's no
yeah, it can be
subjective. So you haven't compared about whether people really think that the generations are diverse.
Right, exactly, and that's kind of the point, because it's a lot easier to create something that looks diverse but actually only looks at a small subset, and that's kind of that's something that showed up in other contexts as well, like the recent issue with face classifiers having a hard time with people who aren't white males is because, you know, they can do a really good job with a subset of the distribution, and it's not immediately obvious sometimes whether or not that's the case. And that's a case where, you know, in retrospect it is obvious, but it may not be for more abstract data sets. And so we're kind of hoping to have a more automated way of doing that.
Okay, thank you.
I have a question for John. This is more on the metrics and like the criteria of what counts as an ill-posed problem. So I was wondering if you talk a little bit about the presence of hidden parameters and distributional shift and how that would fall into the category of well-posed or ill-posed problems.
When you say distributional shift, I'm sorry, what do you mean?
So I mean that you could have a well-posed problem, but then there could be distributional shift in the sense there's some noise or there's very little parameter change. And can you say something about the relationship between the kind of predictions that you would get? Does that count as an ill-posed problem?
Oh, I see.
Because, yeah.
I think it kind of depends. So you know, if you're talking about having a little bit of noise, that isn't really going to change anything in the sense of whether or not I would consider the problem well posed. Like, you know, we're talking over an internet connection right now, but the signal quality is not perfect, but we can still understand each other. And, you know, if I stutter or something or clear my throat, it doesn't cause a problem. But if you increase the noise to a certain point, eventually you get to a point where the features are just completely, not just, you know, slightly noisy, but completely obscured. And that's the point where you start having to actually recreate those features. And so if we were speaking over a connection that was, you know, really, really noisy, it might get to the point where I might say a word and you might be able to tell it had one syllable, but nothing else about it. And so you would know it was a one syllable word, but nothing else. And obviously, you know, that wouldn't be something that you could reconstruct a conversation based on, but there's kind of a middle ground in there where some of the information is lost and you can't, you know, uniquely determine your solution, but there's still enough that you can say it's definitely not this, it might be this, it's probably this. Mm-hmm. And that's kind of what I mean. Does that make sense?
Yeah, thanks.
Yeah, sure.
Okay. Does anybody else have any other questions for the panel?
Is there, so do you know about the recordings for the previous session, or specifically, like, I'm sorry, let me rephrase that. So Cynthia, do you have, I know your talk was recorded, right?
Yeah, it was.
Did you have in there somewhere about the repository that you'd mentioned? I was going to see if I could go back and find that later, but maybe I should just ask.
Yeah, I already adventured there.
Oh, is it? Okay.
So I know that the slides are available in the repository. I'm not sure about the recordings.
Okay. All right.
Hello.
Thank you.
I will upload the recordings in the website in 1 week or so. And also I know that AAAI also plan to publish the videos. So we will send some email to the attendants, but you can see our website in 1 week or so, and you will get the videos because we need to edit it before.
Okay.
Publishing.
Appreciate it.
I have a question for John. In your explorations of trying to reconstruct the conditions on conditional GANs, when trying to look at that bidirectional you know, capability, what about having the conditions as some kind of representation, perhaps within the same modality? So perhaps some text in an image which actually describes some set of parameters or something like that.
So we never actually got to the point where we could look at problems that were complicated enough to do something like that, because even with really simple problems, we were never able to get the kind of performance that we wanted. You can definitely do that, where, you know, even your conditioning information can be something as simple as a one-dimensional class label, or it could have the same dimensionality as the problem that you're trying to solve. Like, for example, that night today image, there's the same dimensionality in those two sets of images. It's basically just as long as your model can learn it, it doesn't matter. And you can have it be a different channel, or like you said, you could use something like text. I don't, for the applications that we looked at, it makes more sense to have it be something separate that you feed in. But there's no reason you couldn't do something like that. I just have no idea how that would work.
Okay. Thanks. Okay. Does anybody have any other quick questions for the panel? If not, I think it would be a good time to move on.